Folks, welcome back. Let's continue our discussion about the atomic ionic size trend. Okay, I'll use this slide, and I believe you've already tried the three rules on in the next slide. Okay, so I'll use this slide, and we'll work together. Well, rule number one. A cation is smaller or larger than its neutral atom. Okay? In other words, the rule number one, the first part of the rule number one is asking you to compare the cation and its neutral atom. Which one is bigger? Okay? For this picture, it asks you to compare this red sphere and this green sphere. Well, apparently, a cation is smaller than its neutral atom, right? Why is that? Well, the reason is quite obvious, because in order to get the cation, the neutral atom has to lose the electron. Okay, here you lose 1 electron and 2 electrons and 3 electrons. So when you lose the electrons, of course the size of the ion will be smaller, okay, because we know that the more electrons you have, the larger the size. The smaller electron you have, the smaller the size. So a cation is smaller than its neutral atom. Okay. All right. The part two, rule number one. An anion is larger or smaller than its neutral atom. So in other words, it wants you to compare the neutral atom and its anion. Well, as you notice that in order to get the anions, you have to get electrons. Okay, for instance, oxygen get 2 electrons to get to become O2 minus. Sulfur to get 2 electrons to become S2 minus. And when you get electrons, the size will increase. Therefore, an anion is larger than its neutral atom. Okay, so as you can see, that 140 is larger than, it's greater than 73, so because you're getting more electrons. All right, rule number one is quite straightforward. Rule number two, in the same group, ionic size increases or decreases from top to bottom. Well, in other words, let's just use this as an example. Lithium plus, sodium plus, potassium plus. When you go from top to bottom, does the ionic size increase or decrease? Well, from the data you can see lithium, sodium, potassium, the size increased from 60 to 95 to 133. Okay, similar trend can be observed on some other groups. Okay, for the group 2A, increased from 31 to 65 to 99. And for the anions, shows you the similar trend. O2 minus 140, S2 minus 184, selenium 2 minus 198. Okay, so it looks like for the same group, ionic size will increase from top to bottom. But what is the reason? Well, the reason is exactly the same as the atomic size trend for neutral atom. Well, as far as we can remember, for those elements in the same group, when you go from top to bottom, atomic size increases, right? Same thing here, when you go from top to bottom, in the same group, ionic size also increase. Again, it's because of the electron increase. You get more and more electrons when you go from top to bottom. Okay, if you happen to remember the electronic configuration that we had for lithium, okay, this is helium. Okay, electronic configuration for lithium 2+. And so it would be 2 electrons. Let me label it here, 2 electrons. And the electronic configuration for an A+ is neon. That is going to be 10 electrons. And I don't know whether you tried the potassium plus or not, But if you tried, then you will realize that the electronic configuration for potassium plus is argon. Okay, how many electrons you have for argon? 18 electrons. So as you notice, from top to bottom, you get more and more electrons. That is why for ions, the size will also increase. This is the rule number 2. Rule number 3. Okay, rule number 3 is a little bit tricky. Now, part 1 for rule number 3. In the same period, cationic size decreases or increases from left to right. Or in other words, it wants you to compare the lithium plus, beryllium 2 plus, and boron 3 plus. When you go from lithium plus to boron 3 plus, what's the trend for the ionic size? Well, from the data, you can see that, okay, it's decreased. Okay, it decreases from your left to right. But what's the reason? Okay. Well, in order to figure out the reason, we do have to consider the electronic configuration again. For beryllium 2 plus, the electronic configuration is also helium, right? As we discussed in a moment ago. And for boron 3 plus, it is also helium. In other words, these 3 ions, they have the same electronic configuration. For magnesium 2 plus, it's neon. Aluminum 3 plus, it's neon. Okay, so as you can see that in the same period, those cations, they have the same electronic configuration. What does that mean? It means that we cannot compare the size of those ions by comparing the number of electrons, because this one, lithium plus 2 electrons, beryllium 2 plus 2 electrons, boron 3 plus still 2 electrons. Okay, so they have the same number of electrons. Okay, so what should we do? Well, if those ions have the same electrons, then you compare protons, right? Well, take a look at the number of the protons for lithium. It is going to be 3, okay? Let me write it here. Proton equals to 3. For beryllium 2 plus, proton equals to 4, right? And for boron, proton is 5, okay? Well, you think about it now, although they have same number of electrons, they have different number of protons. And the more protons you have, the greater attractive force those electrons will experience. Okay? In other words, when you go from lithium plus to boron 3 plus, the 2 electrons will experience the greater and greater attractive force from nucleus, because lithium plus, it has only 3 protons, but for boron 3 plus, it has 5 protons. So those 5 protons will pull the 2 electrons towards the center. So the boron 3 plus will have smaller size, and the lithium plus has a larger size, okay, than the other 2. Okay. Similar reason for the trend of sodium plus, magnesium 2 plus, and aluminum 3 plus. All 3 of them have 10 electrons, okay, neon, okay, 10 electrons. Now, if you consider the number of protons, for sodium plus, the number of the protons is 11. For Mg2 plus, number of proton 12. And for aluminum 3 plus, proton 13. Again, the more protons you have, those electrons will be better attracted. So these electrons will closer to the nucleus, so the cation will be smaller. Okay, so 95, 65, 50. Okay, so for the first part of the rule number 3, cationic size decreases from left to right. Now, the part 2 of rule number 3, anionic size decreases or increases from left to right. Okay, well, let's take a look. O2 minus 140, F minus 136. Well, it looks like when you go from left to right, the anionic size decreases, right? How about this S2 minus and the Cl minus? Again, it decreases when you move from left to right. Well, what's the reason? Again, let's take a look at the electronic configuration of O2 minus. Okay, it's neon 2s2 2p6. For F minus, it's neon 2s2 2p6. For S2 minus, neon 2s2 3s2 3p6. For Cl minus, it's neon 3s2 3p6. Okay, now for O2 minus, as you can see that it will have 10 electrons. Same thing here for F minus, 10 electrons. Okay, now looks like for both O2 minus and F minus, they have the same number of electrons. Okay, so you cannot decide which one is bigger or smaller based on the number of electrons only. Okay, what should we do? Again, like we did for cations, we consider the number of protons. Okay, for O2 minus, the number of the proton is going to be 8. Okay, for F minus, number of proton is 9. Okay, again, because F minus has more protons, these 10 electrons will experience stronger attractive force from the protons or from F minus nucleus. Therefore, those 10 electrons will get closer to the F minus nucleus. F minus would be smaller than O2 minus. Okay, so the more protons you have, when you have two ions with the same number of electrons, now you compare number of protons. The more protons you have, the smaller the ionic size. All right, now let's work on the S2 minus and Cl minus. From the electronic configuration of those two ions, okay, both of them will be 18 electrons. Okay, 18 electrons. Again, since they have the same number of electrons, let's consider the protons. For S2 minus, the number of the proton is going to be 16. For Cl minus, number of proton is 17. Again, the more protons you have, this 18 electrons will experience greater attractive force from Cl minus nucleus. Therefore, Cl minus will have smaller size than S2 minus. Okay, and same thing can be used to explain why Br minus is smaller than Se2 minus. Okay, so for the second part of rule number 3, anionic size decreases from left to right. Okay, and this slide shows you the summary or the answers of those blank those blanks. Okay, so I hope this will help you see the trends better. Now, we've already talked about atomic size trend and ionic size trend. Now, let's talk about first ionization energy trend. Okay, well, this is from your textbook, and these numbers are first ionization energy. What is the first ionization energy? How do we define it? Well, here, let me write this down. First ionization energy means that you remove one electron from a neutral atom, how much energy you need to pay. Okay. Well, the general equation is you remove one electron from neutral atom X to generate X plus cation. Okay. Of course, the electron would be the other product. Well, in order to do this, you need to pay energy. How much energy you have to pay to generate X plus is called first ionization energy. For instance, the first ionization energy of sodium is 496 kilojoule per mole. So that means for sodium, in order to remove one electron from sodium to generate sodium plus, you have to pay 496 kilojoule per mole. Okay, this much of the energy. Okay, now take a look at the trend of the first ionization energy. For those elements in the same group, when you go from top to bottom, ionization energy will decrease. Okay, for the second group, beryllium to barium, same thing. Okay, so the number is getting smaller and smaller. Okay, so this is the first trend for those elements in the same group. The second trend is going to be for the elements in the same period. Okay, if you go from let's just use the second period as an example. If you go from left to right, overall the ionization energy increases. Okay, again there are some exceptions. For instance, beryllium and boron. Boron actually has lower first ionization energy than beryllium, but we are looking at the overall trend. Okay, overall trend still shows you the increasing trend. So these are the first ionization energy. Okay. The last trend that we are going to talk is electron affinity trend. Okay. Well, what is the electron affinity? That means the energy that you have to pay in order to generate an anion with one negative charge. For instance, for chlorine, this is neutral chlorine atom, you provide one electron to generate Cl minus. How much energy that you have to pay? And that energy is called electron affinity. Okay, and here in this table, it shows you that that's going to be negative 349 kilojoule per mole. Okay, well, don't worry about the negative sign here. Okay, later on when we talk about thermodynamics chapter, we will talk about the signs of those energy. But here, you just need to know that this is the energy that is associated by this equation. Okay, the higher the number here, the greater electron affinity the neutral elements will have. Okay, now let's take a look at the trend. Well, for the elements in the same group here, okay, it looks like when you go from top to bottom, this number is getting smaller, okay, from 73 to 47. That means when you go for the elements in the same group, when you go from top to bottom, electron affinity will decrease. Okay. All right, now how about the elements in the same period? Let's use this period as an example. When you go from lithium to fluorine, as you notice that the number is overall trend, the number is increasing, okay, from your left side to right side. That means when you go from lithium to fluorine, the fluorine has a higher electron affinity than lithium. Okay, similar trend can be observed for this period. For instance, from negative 53 to negative 349. Okay, so from your left to right, electron affinity increases. Okay. Again, there are some exceptions here. Okay, but like we mentioned for the other trends, don't worry too much about those exceptions. Focus on the overall trends. Okay, so these are the trends for electron affinity. All right, let me know if you have any questions.